My name is Ron Pressler. I work at Oracle's Java Platform Group. That's a group that develops OpenJDK and designs a Java platform. And I've been asked to tell you that we're hiring in Europe in Dublin, Stockholm, and Prague. That's a new office we have. I serve as the technical lead for Project Loom. It's one of the big OpenJDK projects. And that is what I'm going to talk about. First this, just to say that everything I'm about to tell you is a lie. Okay, so Java is often used to write server applications. And those serve many concurrent incoming requests and also send out requests to other services. And for a long time, we used to write such applications as follows. When a request comes in, it is dispatched to a thread, and it holds on to that thread for the duration of the entire request. Processing the request might involve a lot of waiting for I/O. You might want to read from a socket or through some database API. Or you want to write responses to sockets. And we call that kind of code that starts and ends the request on a thread synchronous code. And it's quite easy to write and debug. And in fact, the entire language and the platform, including all the tools, the debuggers, the profiles, etc., and in the language, the control flow, the exception handling, everything is built around that model. So it fits very nicely, and it's easy to write and profile, but it doesn't scale well. And the reason for that is that threads are megabyte scale entities, and we can only create a limited number of them. And we are limited in the number of things we can do concurrently, even if we have, even if our CPU can spare some more processing cycles, and even if our machine can handle many more open sockets. So it's a programming style that's very nice for the programmer, but it doesn't really make good use of the hardware. And because of the scalability limitations, more recently, people have started writing server applications in an asynchronous style, sometimes using so-called reactive frameworks. And reactive and asynchronous APIs let us express a sequence of operations like do this, and then do that, and then do the other thing. But each of those, the entire processing is not tied to a single thread. Each of the stages can occur in a different thread. And in fact, it recreates the basic building block of the language of writing one statement after another inside its own domain-specific language. So because it does not make use of so many threads, which are a limited resource, it is actually very scalable. We can handle as much as the machine would let us. But the asynchronous code, it fights both the language and the tooling. It's harder to write, I think. It's certainly harder to read. Sometimes the framework ceremony obscures the business logic, and it is nearly impossible to profile, because the profilers assume that the thread gives you some context. And here you have some transaction context, a request context that's not tied to a thread. So the way we represent the application domain, the request, is very different from how the Java platform assumes we represent units of concurrency, which are threads. So the scalability is quite good. The hardware is, we make good use of it, but the programmers are not so happy. And this means that programmers are faced with a choice, with a dilemma. They can either write code that makes them happy, but not the machine, or the other way around. But unlike the really difficult dilemmas in our lives, the source of this one is entirely technical. And it is that currently Java only offers one implementation of threads, the one that is provided by the operating system. And the operating system needs to satisfy many different requirements. It needs to support many different kinds of operations on threads. So one of them could be, one process can run transaction serving server on its threads. Another could be, I don't know, encoding a video. And those two perform very differently, and they require different scheduling algorithms, but the OS has to be good for, sort of okay for all of them. So it's kind of a compromise. In addition, it needs to support all programming languages, and it doesn't really know about how they store data on the stack. So it has to be very general. And this means that it is footprint heavy. Again, the stack is measured in a few kilobytes or up to megabytes, and it can only grow on page granularity, which is 4K. And once it grows, it can't shrink because, again, the OS doesn't really know how your language uses the stack. So it's not that the abstraction that we're using, the language construct, is wrong. It's just that the implementation that Java has provided so far is inadequate to what we want to do. And that is the only reason why we're forced to use models that don't fit quite nicely with the language and the platform. So I said it's a technical language, a technical problem, and luckily it has a technical solution. Just provide a more lightweight kind of thread. If the number of threads, if we're able to make the number of threads essentially unlimited, then we can again represent the application domain's units of concurrency, say the request or the user of the session, whatever you want, as the software unit of concurrency, which is the thread. And this way, the tooling and the language can be happy, and you can make good use of your hardware as well. And this alone would make writing scalable concurrent applications much easier. So just if we were able to do just that. And we thought that we are able to do that. And the Java architects gave the Loom team the task of rethinking how threading and concurrency in general is done on the Java platform. So at the most basic level, the platform provides lightweight virtual threads. And those virtual threads are in orange at the top. There are a great many of them, and they are managed by the Java runtime. That's the Java VM and the core libraries, rather than the OS. And those many lightweight virtual threads are multiplexed on a small number of heavyweight kernel threads. So from the perspective of the operating system, you're only running a very small number of kernel threads, but from your perspective as a programmer, you can create as many threads as you like. We will later see how we are able to achieve that. So in addition, under the covers, all synchronous I/O operations, so if you want to do a blocking read from a socket, it is automatically translated by the Java runtime into non-blocking I/O. So from the perspective of the OS, the code that runs is exactly the same code as would run if you were using some asynchronous framework, some reactive framework. And so you get very good use of your computing resources. But from the programmer's perspective, the code is completely synchronous. And so it works in harmony with both language and the platform tools. So we've built a prototype, and here's what we got so far. On the left-hand side, you have the existing kernel threads, heavyweight threads. Each of them requires a couple of kilobytes in metadata, and by default, 1 megabyte as stack. The task switching from one thread to another can take more than 1 microsecond, even as many as 10. And on the right-hand side, you see what we've been able so far to do with these virtual threads. And they require only a couple hundred bytes of metadata, and the stack can grow and shrink. The task switching, we're working on that, but it is certainly well below 1 microsecond. Okay, but what form would those threads take from your perspective as developers writing on the Java platform? How would you interact with them? So on the one hand, we would like to have this thing called forward compatibility. We would like existing code to take advantage of new features that would give it, say, better scalability without you having to do anything. But that means that we have to stick to old APIs to make to represent the new functionality with old APIs. On the other hand, if we have an opportunity to add an exciting feature around threading and concurrency, and people would hopefully want to use it, then we have an opportunity to maybe correct the mistakes of the past, introduce new APIs without baggage, and start afresh with something completely new. So we didn't quite know which way to go, but when we looked at the problem, we discovered a few things. First of all, the use of the thread current thread and thread local, the thread current thread method, as well as thread locals, is entirely pervasive. So if these new virtual threads, lightweight threads, would not support that particular API, very little existing code would actually run. On the other hand, most other parts of the thread API, the thread class itself, is not actually used directly. Most people don't construct new threads with new thread, and they don't wait for threads to complete with thread.join. Since Java 5, we've encouraged people to use the executor interface and the future interface, and most people seem to be doing that. So whatever baggage there is in the thread class, people don't really actually see it. So it's not as painful as we had thought. And in addition, some methods on the thread class have been deprecated for over 20 years, and we can start removing them. Finally, we've realized that we could keep the existing Java-Lang thread class and make it much more lightweight in terms of footprint. And that was kind of the last element that made us realize that we will just continue representing these new lightweight virtual threads using Java-Lang thread class. So now we can implement, and you'll see how, those virtual threads are actually implemented in Java in the libraries, but they are represented as the same Java-Lang thread. And the runtime itself is better positioned to implement those threads than the operating system because it knows much more about your application. It can see what it's doing, and it knows you're running Java code. When I say Java, I mean anything on the Java platform. It doesn't have to be the front-end Java language front-end, so any Java platform language. We can do the task switching from one task to another, from one virtual thread to another, without entirely in user mode, without switching to the kernel, and that's faster. And again, because we know how the runtime stores information on the stacks, we can detect when they need to grow and when they can shrink. What we can't currently do, in fact, we will never be able to do, is we can't support blocking from inside native code, and I'll explain what that means. So things will work. I'll explain the ramifications, but that means that if you're calling to a native method via JNI, and that native method tries to block the thread, it won't actually block the virtual thread. It will actually block the OS thread underneath it. Okay, so that takes care of Java-Lang thread, and like I said, people use it for current thread. That would continue working. So a lot of existing code would just continue working as is, but most people don't actually use the thread API otherwise directly. They use executors and futures. Can we do better over there? And here I think that we can, and we were lucky to find some prior art fairly recent. It's called structured concurrency. The term and the idea was probably invented by someone called Martin Sustrick, but it was well publicized by someone called Nathaniel J. Smith, and those two blog posts on the bottom gave me at least the rare occasion of reading a blog post and saying immediately, that is probably the right way to do it, or at least in the right direction. That is something that happens quite rarely. So it was very convincing, and to other people as well. And we said, okay, let's go with that. So the basic idea behind structured concurrency. This is how we'd want people to write concurrent code in this new world where threads are essentially free. So the main idea is that whenever the control flow splits and you're doing multiple things in parallel, it has to join again before the parent can continue. So like you can see with those arrows, every time it splits, it joins up again before it can split again. And the word structured means that the runtime behavior, in this case the lifetime of each of the individual threads, is clearly mirrored in the code itself. And the code is represented as blocks, and those blocks will show you exactly the lifetime of those threads and exactly where they split and where they join again. We have had structured concurrency API in the Loom prototype. The decision to represent the new virtual threads as Java lang thread is very, very recent, like made about two weeks ago. So we currently, with this new direction, we don't have structured concurrency yet. We will bring it back. So what I'm showing you here is speculated. It's very similar to what we had before. And the idea is that you have a block in the code, and that block shows you the lifetime of all the threads that are created inside of it. And even though each of these tasks will get a new thread of its own, as you can see, we're not actually using the thread API. And each of those threads starts, when we see those arrows where we call start, but we know we are guaranteed that it will end by the time we exit that scope. How we guarantee that? So it's a try with the resources scope, and it calls a close method on that thing, that temporary I called thread scope, and when it calls that, it blocks and waits for all those threads to terminate. So I know for a fact that once we exit that block, none of those threads would be alive. Now, they themselves can do the same thing and create their own threads. But similarly, they won't be able to return until the threads they created have terminated. So if executor and future were unstructured, we will have these lifetime scopes, and probably each of those start methods will need to return some sort of handle. We don't exactly know what that will be. Could be a future, could be something else. So that will be the structured way of writing code. Just some things that it helps you with. If your current thread, the one that is currently running this code, this block, gets cancelled, we can say that we create the scope with a propagate cancel, and when we are cancelled, the cancellation is propagated. It's similar to interruption. It's a bit of a stronger mechanism. It propagates to all the threads we created within the block. So when you can cancel a whole tree of threads, but you know that they're all working on the same transaction because everything is structured. You know exactly where everything starts and where everything begins. And if you think about it, one of the things it automatically gives us is good error handling. One of the problems with unstructured concurrency is that you create a thread, and the method returns there is some thread that lives out there. Maybe someone will join it. Maybe no one will. But what happens if there is an exception on that thread? Maybe you remember to handle exceptions correctly. Maybe not. Here, because we know exactly where the threads start and where they end, we can propagate the exceptions up to the calling thread, and then you can get to decide what to do with them. It's a bit similar to how I think they're called supervisors in Erlang. A bit kind of like how they work, but maybe better because it's structured here. So this gives you a very nice, and it looks like that. You see your control flow goes in, you have one thread, then it splits into two, and then when you exit that block, it's one again. Another thing that is very difficult for programmers to manage is deadlines and timeouts. If you want to do some I/O operation, you usually want to not wait forever. And managing those timeouts is actually quite difficult because you have to say, okay, if I started out with, say, 5 seconds, now I have to look at the time again, maybe I only have 3 seconds left, and then you do another operation, you retry, and then now you only have 3 seconds left. So this helps you also work with deadlines. You can just say that this entire scope must complete in 30 seconds, and if not, then those threads will be cancelled. And either way, we will block and wait for them to finish. So we know when we exit the scope that they are finished. Okay, another subject that interacts strongly with how we work with threads is thread local data. It's not just actual thread locals, but some other stuff. We have the context class loader, we have access control context, something has to do with security, but I will just focus on thread local. As many of you have probably experienced, thread locals don't play nicely with thread pools where one thread is shared by many different tasks, because then the scheduler has to know when it starts executing one thread and then execute another, it has to replace all the thread locals, and it doesn't quite work. But that problem is immediately solved just by the fact that now it's cheap enough to run every task in its own thread. We can create thread, we can block them, and we just don't need to care too much about costs. There are a couple of other problems. First of all, thread locals are mutable. You can assign them and reassign them however much you like. We'll see how we could do it better if we are no longer mutable. And the other thing is we're unstructured. So like in the case of threads, when a method creates a thread, you never know you never know when it terminates, and we like this structured way of looking at things. If you look at your code, you know where some scope begins and where it ends. And with thread locals, you assign a thread local value, and it's in effect indefinitely until someone sets it to some other value. And finally, it's completely dynamic. So even explain what I mean by that. Even though thread locals are more special than ordinary variables, and they are used much more rarely, you can create new thread locals completely dynamically, which is something that you can't do for ordinary variables. Right? You can't create a new static, a new instance member or a new static member or a new local dynamically. But with thread locals, you can. And that actually, even though you don't really need to, and that actually makes them not as fast as they could be. So, an idea we're exploring as a better alternative to thread locals will still be available, but we think this is better, is something that we call scope locals. There are many languages with a similar construct. On the Java platform, we have closure with dynamic variables. That's the exact same idea. We didn't invent this. So we start by declaring the variables. Here, we just basically create them similarly to thread locals, and they could be dynamic, but maybe we'll do something else to make it faster. And then we assign them, again, inside a try of the resources block. You'll see that the way it is actually written is not currently valid Java, because Java requires that you assign the return value from any calls inside the try of the resources header to some named variable. But let's assume that we could change the language. And you would bind, what you can do with scope locals is you bind them. And once you bind them, that value you bind them to is in effect for the duration of that scope, and they're accessible anywhere inside that scope, even inside other methods, just like thread locals. So we bind s1 to 1 and s2 to hello, and we call another method we call foo, and inside foo we just get them, and it would print hello 1. But to show that that the lifetime of these assignments is a scope, let me show you another example. In this example, we have two nested bindings. In this case, they are in the same method, but they could be anywhere inside the stack. So first we bind s1 to 1 and s2 to hello, and we call foo, and it would print hello 1. Then we bind s1 to 2 and s2 to goodbye, and we call foo again, and inside that scope, foo would print goodbye 2. But once that scope ends, we are now inside the enclosing scope. So we're back to that scope's value. What happens if we are in a scope where there are no bound values? Probably an exception. So you can rebind a scope local inside a nested scope, but you can't mutate it. So you can rebind it. It's in effect within that scope, but once you leave it, it remembers the old value. So why is that important? Because it works very nicely together with structured concurrency. Because these values are immutable, they can be shared by all the threads that are created inside the nested structured concurrency scope. And because we know that all those threads will terminate before exiting the nested scope, and therefore before exiting the enclosing scope, we are guaranteed that none of them would see the value changing on them. So it's safe to put, so you could put, for example, the transaction identifier in a scope like that, spawn many threads that would do, say, calls to microservices or to the database, and all of them would be able to access the thread local transaction ID, even though it's sort of a parent thread and not their own thread. So it's a little bit similar to inheritable thread locals, but structured and with good guarantees that the value of the scope local would be in effect. So we believe that scope locals would be able to supplant most uses of thread local, maybe not all of them. Another thing we're exploring is something called processor locals. Sometimes it's not, normal applications don't use that kind of thing I'm going to describe, but very efficient concurrent code may want to associate a data structure for concurrent striping. Like if you want a counter, a concurrent counter, you want to associate a bit of data with any processor. So today, you can just do it as a thread local and say that threads are sort of an approximation to processors. And that works okay if you have, say, 30 cores and 200 threads, or 2,000, but not if you have 2 million. In that case, it just becomes very, very wasteful. So we're exploring something to that will let people associate some data with the current CPU. And even though most people will just be using the structured concurrency mechanism, some people may want to customize it, and they would use a thread API directly to create threads. And instead of just having one flavor of thread or two, because we have daemon threads today, we'll have a whole kind of flavors that you can choose from. You can choose it to be a heavyweight kernel thread. You can choose a virtual lightweight thread. You can turn on and off, on or off certain capabilities, such as supporting thread locals. You can say that you know that your thread won't be using thread locals, so you don't want to pay the extra footprint, and you can turn off just inheritable thread locals, etc. Okay. So that's what I had to say about the new threads that Project Loom introduces. And now, just to satisfy your curiosity, just to spend some time on how they're actually implemented under the covers. So you don't need any of this to actually use the new threads, but if you're curious to know how we've actually implemented them. So we start with a new mechanism that is exposed by the actual VM, that is called continuations, more technically delimited continuations, and there are many kinds of those. And they are not currently exposed as a public API, but you could think of them as if they have this API. And you create a continuation, you can ignore the scope. You give it a runnable body. That's the code that's going to run inside the continuation. And the two most important methods here are run and yield. When you run the continuation, it will start running any code that's inside the body until it calls yield. When the continuation calls yield, the run method would return to the caller. The next time you call it, instead of starting anew, it would continue from the last point where it yielded. So let me show you an example. Suppose that is our continuation. It prints before, then it yields, and then it prints after. The first time you call run, it prints before and then returns, and it says that it's not done. The second time you call run, it will print after, and then it would also say that it is done. One important thing that's important here that is different from other languages like Kotlin, the code that runs inside the continuation does not need to be marked in any way. It's ordinary Java code, and you can call yield from any depth in the call stack. Okay, so now that we've seen continuation, let's go back and consider what a thread is. So a thread really requires two things. It requires the ability to run something and then yield control, right? You say to the operator, so let's talk about kernel threads. You do some I/O operation, and then you say, okay, I've used the CPU enough, now I want to wait for some I/O, in which case the operating system will remove your thread from the CPU and schedule another thread on that CPU. So a thread requires the ability to suspend your execution and then resume it. In addition, it requires some mechanism to decide when and on which CPU core to execute your code, and that is called a scheduler. And that is exactly, so the first mechanism, the ability to yield and resume, is exactly what continuations do. And for the second mechanism, to decide when to run those continuations, we could just use any Java scheduler, even existing ones. So we take the continuations that are provided to us by the VM, and we implement these virtual threads in Java in the core libraries using schedulers, ordinary Java schedulers. So let's run through an example. Let's suppose you run some code, and then it tries to acquire a lock, a Java util concurrent lock. And the lock is unavailable, so it has to wait. And the way it is currently done, all the places in Java util concurrent that wants to wait call this method lock support park. And what you used to do, you used to call this on safe.park, and that just asks the operating system to suspend the current thread. But now what we do is we can see if the thread is lightweight. What we do is just we yield the continuation. When we yield the continuation, the runnable that the scheduler is running will just return, even though it's suspended. The scheduler would just think, okay, you've run a task, now it's over, now I can run something else. The next time it will run it again, it will continue. When we release a lock, we pick the next thread that is waiting in the queue, and we unpark it. And so now, if it's a heavyweight thread, we just ask the kernel to unpark it. But if it's a lightweight thread, all we have to do is to take the continuation that's inside that virtual thread, submit it to the scheduler, because remember, continuation is just a runnable. Any scheduler you like, it will just execute it. But the next time it executes it, it won't start anew. It would continue. So let's see what it looks like. Suppose we have this very large stack trace. We are running inside a fork join pool, and that is currently the default executor for these virtual threads. And when you run code that is inside virtual threads, so where on the bottom, the yellow color, where that ends, that's part of the scheduler. That's code that runs as part of the scheduler thread. it enters a continuation. And then it runs user code until it yields. And once it yields, what happens is that all the frames between the yield and enter get removed from the stack, and then those run and run continuation methods return, and now the scheduler is just in its loop, and it's ready to run another task. And it doesn't even need to know that it's a lightweight thread. It's just a runnable. So if you recall, so now it wants to run another runnable, and if you recall what we saw is that if someone else now releases that lock and unparks our thread, it would just submit it back to the scheduler, and the scheduler would encounter it again in its execution loop, and it will just see it as a runnable. But as soon as it wants to continue it, as soon as it would call continuation.run, all those stacks, our entire state that was suspended, would get reincarnated, and the call from yield would return, and we would be outside lock, and we'll be able to continue. And the exact same thing happens with I/O. So we've replaced the implementations of I/O to be written in Java, and now it actually does non-blocking I/O, but when it waits for an operation to complete, it calls park. So it's the exact same mechanism. Those stacks would just be removed, and we can run another task. Okay, so continuations have a couple of limitations at the moment. So the first is they cannot yield when there is a native frame on the continuation stack. Like I said, if you call into some code that's written in C, we don't know exactly how to remove that frame from the stack. And so that limitation remains forever. And we can't yield while we're holding a monitor. So while we're inside a synchronized method or a synchronized block. That is a temporary limitation. It will be removed eventually. For the time being, if you just use Java util concurrent locks around those places where you're doing I/O, so if you guard your I/O operations with synchronized, and you want it to perform well with Project Loom with these virtual threads, please replace synchronized blocks or methods with Java util concurrent locks. So what's our status? All the code in Java util concurrent just works, but it does require retuning. For example, when you want to acquire a lock, because parking a heavyweight thread is an expensive operation, the code there tries to postpone that, and it just spins. But suspending virtual threads is very quick, so we need to calibrate it. If you do thread.sleep on a virtual thread, no actual kernel threads would be blocked. All the Java.NET, the socket, server socket, they are now implemented in Java, so they would work with Project Loom threads, and that change has actually gone in JDK 13. The NIO code, socket channels, actually had gone in earlier. We have TLS. There are two cases in the JDK itself where we might have a native frame on the stack. One of them is in the access controller when we want to do privilege if you're running with a security manager. So we've replaced that with a Java implementation. And the last one is reflective invocation of methods. So right now we have, so the way it works is reflective invocation first goes through a native method a few times, and after a while it just spins out Java bytecode. So what we've done so far is just, if you're running in a native thread, we spin out the bytecode sooner or immediately the first time, but we might be able to make that better. But I said that if you're inside a synchronized block or in a synchronized method, or you call object.wait, we cannot yield the continuation. So what happens? What happens if you try to do that is we say that the continuation is pinned, and the runtime will detect that and will actually block the kernel thread, and that would be the scheduler's worker thread. So your code will work, but it won't have the same scalability. And it's okay if it happens from time to time, but if you guard all your I/O operations all the time with synchronized, then you might want to consider replacing it or waiting until synchronized is supported. Native frames, that is a way it remains forever. If you call into C, and then even if you come back into Java and you try to block the thread, it's going to be the underlying kernel thread that would be blocked, not the virtual thread. We have debugger support, and one thing we are missing is currently in our Java implementation of DNS lookup. I think that should be done quickly. So if you call inet address to resolve a server name, currently that's written natively, so that will block the kernel thread. Console I/O is not ready. File I/O, that depends on the operating system. We'll see what we can do. One thing we might add is channels, similar to what they have in Go. And we've started working on JFR support for profiling. If you have never used JFR, who here uses JFR? Okay, that's terrible. That, in my opinion, that is maybe certainly in the top 2 reasons to use Java. It's very low overhead and very deep profiling in production. You can just profile your application all the time. It gives you very detailed information at basically 0 cost. I think it's like 1%. So please use JFR. And most of the good profiling of Java code should go through JFR. We would like to support those threads. And we are improving performance. And now I'll left some time for questions. Let's see. Hang on. Yes?
How many people work on Loom?
How many people work on Loom? So full-time, it's about 7, I think. But other people, so for example, the DNS lookup implementation, we've spawned that off to the networking team. So certain areas, if we see that people don't really need to know how the virtual threads are implemented, they just need to implement something in Java. So that's people outside the Loom team work on it. But
when do you think it will be ready? Which version?
When do I think it will be ready? I don't know. But it will be delivered within 6 months from the time it is ready. We honestly don't know.
Okay, and last question. You don't speak of some code that will calculate a long time. Is the JVM...
Very good question. Okay. So what about code that is CPU heavy, that's not doing I/O operations? So if you do that in kernel threads, what's going to happen is that after a while, kernel threads are preempted when you do I/O, when you synchronize on mutexes, and after a certain time slice. We could quite easily implement time slice-based preemption because in Java we have the save point mechanism. We need the ability to basically stop all threads just to do certain parts of GC. So it's very easy for us to say, okay, please stop. But there's a question whether that would be useful at all. The reason for that is, if you have 30 cores and say 100 threads, and say 90 of them require a lot of computation, the scheduler can say, okay, you've run for all this while, I don't know, 5 milliseconds, I'm going to run another one. But if you have 30 cores and 5 million threads, and say 1 million of them require a lot of computation, then there is nothing a scheduler can do, you're just under-provisioned. So it would only work if only a very small number of these threads would actually do calculation. And in that case, either you know those threads in advance and you can just run them inside heavyweight thread, and you are guaranteed it's a small number, because if it's not, then you're screwed. And the other option is that many threads will try to do that, but not at the same time, occasionally. And that works already because we use a work stealing scheduler, and it's going to detect that automatically and just move stuff to other cores. So it seems like it's not going to give us a lot of benefit. We could do it, but I don't see the benefit. It's very important languages where this is the only kind of thread they give you. But here you can still choose, please give me a kernel thread. Yes? Again, what users? Parallel streams. No. It's a bit complicated. So parallel streams are meant for parallel computation. You want to, I don't know, invert a matrix or do some machine learning. These lightweight threads are meant for transaction processing and concurrency and I/O. So they're they're different use cases. Whether we be able to find a way for both of them to somehow interact in some interesting way, that remains to be seen. But they are quite different in their role. So again, parallel streams is for computation heavy. This is for I/O heavy, transaction processing, concurrency, not so much computational parallelism. Any more questions? You asked already. Say you there in the back, if I could hear.
You had something like green threads.
Right. So back, I think, in Java 1.0, threads were also implemented by the runtime, but those green threads were actually single-threaded from the operating system's perspective. They all ran on one kernel thread. These threads make use of however many threads your scheduler. You can plug your own scheduler. However many threads, kernel threads, your scheduler assigns them. And also the way we write programs and the kind of things that we do changes. So, but you are right that in a way some of that is coming back. Yes. Okay, so you had another question. Yeah, so can I compare our virtual threads? By the way, we started calling them fibers, then we changed to lightweight threads. Now we think it might be virtual threads, so I'm trying to be careful not to commit to anything, so I say lightweight virtual threads. The coroutines in languages like Kotlin and C#, they are intended to serve a similar purpose of writing code that looks synchronous but is actually behind the scene is asynchronous. But in terms of usability, it's quite different. In those languages, coroutines are a syntactic construct. When you write a piece of code, you have to say that this piece of code is a coroutine. It cannot run as a method, and you can't run a method as a coroutine. It's either a method or a coroutine. So you have to say, so in C# it's async, in Kotlin also async? Sus, I think, yeah. Here, you don't need to do that. You just, our continuations are a dynamic construct. You can run the same piece of code either on a kernel thread or another lightweight thread, and you don't need to write the code any differently. And that has very big implications to migrating old code. Much of it would just run and enjoy this better scalability, and also interacting with existing APIs. Because if you want to call an API in C# or in Kotlin, that API is either a continuation or ordinary blocking methods. So they can't take the existing API and make them play nicely with coroutines that they would work exactly the same way. The exact same API, call to read from a socket. If you're running on a heavyweight thread, kernel thread, it would behave just the same way as before. But if your dynamic context is that you're running in a virtual thread, then it will behave like a coroutine. So that is the big difference. Yes, last question.
Is there a reason why you wouldn't expose the scopes API already?
Why don't we? Right. Yes, because we think. So why don't we expose? Wait. Which API? You mean the structured concurrency?
Yeah, the replacement for thread locals.
Oh, no. We will expose that whenever it's ready, and probably together with continuations. With everything else I've shown you. So in the first release of Project Loom, and my time is up. So thank you very much, and ask me later.